Well, hello and welcome YouTube to Mr. Robinson's Q&A Power Hour. Now, I haven't done a lot of these, and this one is not going to be seemingly all that long. I got 2 questions for my Integrated Math 2 students on polynomials. I think specifically more on the factoring portion. I read them back when, I forget what they were now. But we'll take a look at what they are, and listen, I'll stretch this thing out if I need to. I can take the whole hour. I probably will not at all. But things on factoring, if they ask about factoring strategies, I might want to talk about some of those for sure. So if you want to just go ahead and listen in, and you think that you have any things you want to look at here, let's see what the questions are. I'm not going to look right now. I'm just going to keep talking. Let's see. Like that. We'll start there. And then I'll start writing things as needed. Now, one thing I did pop up in case you guys won't see it, but there's an old factoring factory video that I made a long time ago, and it has, let me pop this thing up. I had to do all this. It had 278 questions of just asking to factor of all different varieties and sorts, and some which are not covered in Integrated Math 2, including factoring by grouping. Well, actually it is, but not for my students, but factoring by grouping and using the rational root theorem, so those aren't on there. But anyway, I brought it up because in case I want to find an example, I'll use one of the problems on there and just say, okay, based on this, what can I do? Because I'm not really good at making ones up, or if I make one up, that means I already know the answer to the factorization. So anyway, all that being said, students, start submitting questions to me, man. You should see some of my previous years. I get loads of questions. Something different about the student. Yeah, I'm calling out my students this year for this. Submit me something. Ask me something. If you know it all, great. If you don't, submit it, all right? I'm happily recording a video for you guys. Okay, with that being said, let's go ahead and take a look at the 2 things that were asked and see what we can do with them. The first question, let's see, I get this over myself. The first question that was asked is, what are the easiest ways to remember perfect square numbers? A fun song to remember. I don't particularly know one. If you would like to Google search or YouTube search, I'm sure there will be something. But the reason why this is being asked, let me go to this. This is where I wanted to write. The reason why this is being asked is because when you hit the special case factoring of difference of 2 squares and perfect square trinomials, this is one I can make up. You can get something like 4x squared. I have to actually come up with it. Plus 81 minus, minus 36x. There we go. So if you get something like this, and you're being asked to factor this thing, there's the whole thing about, we got to find product factors of this number, etc. But if you recognize, oh, wait a second. Not only is x obviously being squared as it's a quadratic, but so is 4. And 4 is 2 squared. And 81 is 9 squared. And is this number doubling, 2 times 9? That's what I had to think about. 2 times 9 is 18 and doubled is 36. And yes, it is. And, obviously there's a bigger picture involved. But that's why the reason the question is being brought up is because what I told them was, you don't look for perfect squares. You want them to call attention to you. Because if you sit around looking for something that's a perfect square, you're spending too long on a problem that's probably not a perfect square trinomial or difference of 2 squares. When I test my own students on the stuff, they're going to get like one of each question of that sort, but recognizing it will save them on the one problem so much if they just know what they are. So as far as things go with regard to your particular question, is there a way to remember them? I mean, knowing your times tables would be a good way to ask yourself, what is 1 times 1, 2 times 2, things like that. But even furthermore, when you get your test, this is just for anyone, if you get a test or something like that, who's stopping you from writing this at the top of your paper? All these things here. I mean, they can just keep going. 7 times 7, 8 times 8. Whoops, I was starting to write 8. 8 squared, 8 times 8, so 64. And then 81 and 100. There are a couple ways I'll show you how to calculate these. If you don't, maybe you can use a calculator as well. But 121, 144, what am I going? 12 squared, 13 squared, 14 squared, 15 squared, 16 squared, 256, 289, 324, I think, 361. I think that's 324, 361, 400. That goes all the way to 20 squared. Anyway. So you can also use a calculator to compute some of those things. One interesting thing about perfect squares, and I'm going to start from 0 as an example of that, is that if you notice there's a pattern on how they increase. Here you add 1, here you add 3, here you add 5, here you add 7, things like that. And you could actually come up with, in a way, like a formula for asking yourself, because you'd have to know, hey, what number am I adding from here to here? Because you have to know what thing you're on. You can come up with a whole formula and things like that. So there's that pattern. on perfect squares that the difference between their difference is common. They're all separated by 2. You add the next odd number up. There's that. And also, this goes back to your whole, squaring something like that. A plus b squared is a squared plus 2ab plus b squared. If you didn't have a calculator and I had to do something like 21 squared, I can do 20 plus 1 squared. And I'd have to know 20 squared to begin with, but that's 20 squared plus 2 times 20 plus 1, or times 1 plus 1 squared, which is 400, plus 40 plus 1, which is 441. So there are a lot of ways you can calculate them. But the real question is how would you, to remember them, how you know them. You just got to familiarize yourself with them. At some point, you know them through times tables. I mean, you start doing times tables, I assume, in 3rd grade. And then you build up through that over time. And it's a familiarity concept. I see the number 121, and the first thing that calls attention to me on it is that it's a perfect square value, that's just what it is. It's 11 squared. I see 25, and I just know that it's 5. That doesn't mean those are the only 2 factors. Obviously, 25 and 1 are other factors and things like that. 64 is billions of factors, a bunch of factors. So does 256. But they call attention to me so that when I see my first term and my last term are both perfect squares, it's possible that the whole thing's a perfect square trinomial. And that test can help speed up those individual problems instead of trying to test for some other things, because then you know what the answer absolutely is. Furthermore, when you have a difference of 2 squares, when you have 2 terms as squares, an x squared term, and then subtract it, something x squared minus something, I mean, outside of a greatest common factor getting you to perfect squares, they probably are perfect squares if you're being asked to factor. Because that's the only way that that's going to happen, to create that factorization. Difference of 2 squares is very specific factorization that cancels out the middle terms, and they only cancel out if you're multiplying the same bits of things twice. So those have to be perfect squares within. So there's also that as well. So I don't know if really that's answering the question. There's no specific song. You can write out the list. You can know the list. Use a calculator for the list. But you want the point is you want them to call attention to you so you know what they are. And really, you got to familiarize yourself with them. That's just the big thing. Once you learn times tables, you move on forward to say, do I know them? Yeah, 13 squared, 14 squared. Not a lot of people know as much. You're supposed to do your times tables up to 12, so those are supposed to show up. 15 and 16 are a little more common than 13 and 14, so hey, maybe they do, maybe they don't. 15 less than 16, but they still do. Anything that ends in a 5 can have some commonality. Anyway, so that's it. As I'm stretching out this Power Hour video, I hope that answered it in some sort of good way. Thank you for asking the question. All right, and the next question is, when we factor, how do we know when to apply each method? Thank you, Mr. Robinson. Well, you are very welcome. The methods that we talk about, well, here's the thing. All the methods really are the same. We might talk about them differently because of our needs for them. And here's where I can probably spend a lot more time talking about this on a breakdown. So let me start with this. Let's look at what foiling, multiplying something out, provides us when it comes to this binomial times binomial to make a quadratic trinomial. And keep all this in mind, by the way, guys. You always find greatest common factor first. So maybe all that exists is the greatest common factor. So when it comes to methods, greatest common factor rules all. Now, I just came from a previous question where I was talking about how, you want perfect squares to call to you. Greatest common factors, you just got to, well, sometimes you got to know if you can divide by something, but you want to look for them first, period. Because they happen a lot, and then we just go from there. But anyway, let's make up something. Let's make up x minus 10 times x plus 4. Okay, I'm going to take this and multiply this thing out. Now, what happens when you multiply this thing out is x multiplies with x, and you get x squared. X multiplies with 4. Now, more importantly, it's 1x. 1x multiplies with 4, and you get 4x. Negative 10 multiplies with 1x, and you get negative 10x. And negative 10 multiplies with 4, and you get negative 40. Then 2 terms combine, these 2 inner terms, if you write them out in FOIL method, first, outer, inner, last, whatever. 4x minus 10x is negative 6x, so you get x squared minus 6x minus 40. Now, I bring all this up because if you went from here to factor, if you went in that method, in that direction to factor, you notice that the last 2 terms that multiplied, these guys, became the last term there. Now, that's always going to happen when it comes to whatever method, no matter what. Assuming no GCFs or all GCFs are out of the way. The last two constants will multiply to become the constant. Nothing else will combine with it. And those are the last things that happen to distribute. Method-wise, no matter which kind of multiplication you're looking at, that's always going to happen. Now, the very particular thing about a problem like this is this was an x times an x, which gave me an x squared. A 1x times a 1x giving me a 1x squared. So in this case, a 1 times 1 equals 1. Now, this one is so basic. This one is very simple. This one allows us to have very little thought as far as what the first term is broken up to. It'll only be broken up into x times x, which also makes things very easy. So we are trying to create a factorization like this based on what we have. Sorry, this should say 1x. Based on what we have here, knowing that it's going to be an x times x principle. Knowing that the last two terms are going to multiply to the last thing here, but there's more than just 4 times negative 10 that multiplies to become negative 40. Heck, negative 4 times 10 multiplies to become negative 40. So does 8 and negative 5, or switch those signs. So does 20 and 2, and that might be it, and 40 and 1. So there are different ones. So how do you know which one to choose? Well, this is where every method has the same thing, but again, this one's easier. You also need these two numbers in this particular case to add to become negative 6, as in 4 plus negative 10 plus 4, whatever it is. They need to become negative 6 as a whole because of how these two combine using that FOIL method. Notice that the outside and the inside add together to become that middle term. Now, I'm talking about this method for a big reason. It's because of what we did through FOIL. Remember when I said that this wasn't just x times 4, it's 1x times 4? And this isn't just negative 10 times x, it's negative 10 times 1x. The 1 in both of these does not change this coefficient. 1 times 4 is 4. 1 times negative 10 is negative 10. 1 times a is a. 1 times b is b. Whatever you are multiplying 1 by will be the result of that number, of that coefficient. So whatever this number is, and whatever this number is, are the ones that are going to add together to become this, when these are just ones, because these won't change their value when multiplied out. So in these problems, the reason we started with those diamonds to say what two numbers multiply to become this and add to become this through factorization is because these two numbers represent the answers, the portions that appear in your answer here. Because they don't change, because they aren't affected just by multiplying by x. Yeah, they have an x on it. I don't care about that. They're going to combine. That's the only reason. That's the only thing I care about there. But the numbers themselves don't change because they're really just being multiplied by a 1. Okay, now keep all that in mind. All that factoring biz is what we're going to apply to the next thing. The difference is I won't draw a diamond because the diamond isn't the answer. So let's do another one. Now, by the way, we didn't ever factor this one. I'm going to do other examples with these, but let's do another one now. Let's look at 3x minus, or plus 7 times 2x minus 2. No, let's do 3. Okay, now let's FOIL this one out. 3x times 2x is 6x squared. Just like x times x is x squared, so that's 6x squared. Now look at this. This next part, when I do FOIL, that outside and inside, is not going to be negative 3 plus 7. Because negative 3 is about to be multiplied by 3. I do 3x times negative 3. That's negative 9x. I do 7 times 2x. That's 14x. And then I do 7 times negative 3, which is negative 21. And then I combine these things and I get, 6x squared plus 5x minus 21. Okay, now the negative 21 still came from 7 times negative 3. That didn't change. So I still need factors of my last term, and those will still end up as the values here. That didn't change from here. You know what else didn't change from here is the first two terms multiplying to become your first term. The difference is this only has one possibility, and this can have more than one. Sometimes it still only has one. The difference is 6 is a composite number, not a prime number. I can multiply 3 by 2 to get 6. I can multiply 6 by 1 to get 6. So how do I know which one's which? Same thing with here. How do I know it's 4 times 10 versus 8 times 5, whatever? Well, these ones specifically had to also add to become negative 6. And these don't specifically add to become anything, but they are going to multiply with your other numbers, factors of 21. So that when you add those outer and inner terms together, they are somehow going to make 5. So 3 times negative 3 became negative 9. 7 times 2 became 14. No longer Do the 9 and the 14, do the negative 9 and the 14 represent values that appear directly in your factorization? They are products. They are products of what you had through foiling. Negative 9 did not appear here. It was 3 times negative 3. 14 did not appear here. It was 7 times 2. And they could. I could have had a 14 times 1 scenario. Not in this, obviously, because that's what the problem was. But I could have had a 14 times 1 scenario. But because this A is not 1, something's going to get affected somewhere. One of your numbers that represents a factor will appear. And that happens here, but the difference is because these are 1s, you absolutely know these will be x's, and you absolutely know that they won't change these values when it comes to adding them together. So that's what makes these ones so easy, and that's what makes these ones ask you to do a little more. But I would factor these the same way. I'd factor this the same way as I'd factor this. I just have to be pickier about what I need to test. I know what's going to be tested here. The two numbers here I got to add together to get that, period, because they're just going to be multiplied by 1. These ones I don't add together to try and get 5. Now 7 minus 3 is 4. That's really close to 5. That's just a coincidence. I'm sure I could even get one that actually where the numbers do add to become it, but it's what these multiply to. And what these multiply to then combine to become that you got to look at. Once again, 4x minus 10x, straight up, those numbers are the coefficients. These numbers are not necessarily the coefficients. At least one of them is going to be affected. So here's where my factoring factory thing will pop up here. I'm going to find a problem just by random and write that one down. I'm going to do one that has an x squared thing on it. I'm going to do one that does not have an x squared thing on it. And then I'm going to let's get rid of these. Excuse me, I'm going to have one with a 1x squared, one that doesn't have a 1x squared. And then let's look at how I can talk about those things. And I won't bring up the diamond thing. That was just making sure we had some number sense. I'll bring it up the same way in both formats so we know exactly what we're looking at. But I get to be faster when it's a 1x squared for a lot of reasons, including future tests. So let me find a first one here. Well, you know what? Okay, here's one with a GCF I just found. It was the very first problem on here. 3x squared plus 15x plus 18. These all have a GCF of 3. So you do want to factor that out first, and when it comes to factoring strategies, you always do that first. You stop at nothing to get a GCF out first. The point is I now need to factor this inside, and this inside is a 1x squared. So that's what we're going to deal with. Now, as far as factorization goes, here's what I'm saying. I know that if this is factorable, quadratic trinomial will be some form of this and all that kind of stuff. Now, if I weren't playing my diamond game and I was doing it more of like how I factor, what are my strategies, I'm going to use these the same way each time. I know that x squared, 1x squared, only comes from 1x times 1x, x times x. I know that from a positive product and a positive sum, both of these have to be added. And I know that 6 can come from 6 times 1 or 3 times 2. Oh, something else I get to mention about this that's so great. In the other problem, let me go back. Oh, I lost it. But in the other problem, if I switched the 6 and the 1, it'll change my result because a different value is multiplying by a different value there. But here, x times 1 and x times 6 is the same thing as x times 6 and x times 1, like that. So I don't have to switch them either, which is nice. So which one's the answer? Is it x times, is it this one or is it the one with 3 and 2? Well, x times 1 is 1x. 1x. X times, or 6 times x is 6x, and 1x plus 6x is 7x, and I want 5x as my result, so it's not that one. So let's try 3 and 2. Imagine there's a plus there. X times 2 is 2x, 3 times x is 3x, and 2x plus 3x is 5x. My goal was to get this thing foiled out. Remember, I was testing factors of x squared. It's just x times x. I was testing factors of 6. There are 2 sets of them. I have already locked in those parts of my foiling aspect. I'm just trying to find which one from the outside plus the inside, when multiplied, boom, boom, gets me my linear combination of 5x. For me, personally, I ignore mentioning x when I'm doing it. I'm just looking at 1 plus 6 and 2 times 3 because I already know that they're just multiplying with an x, and I know that they are going to be able to combine. So 6 plus 1 is 7. No. 3 plus 2 is 5. Yes. That's why when we ask what two numbers multiply to 6 and add to 5, we know that those are the answers as well because they aren't affected by 1s. And that's it. So it's x plus 3, or 3 times x plus 3 times x plus 2. And once again, if you want to see me do this in my factoring factory video, I've probably already, through my whole explanation of this, I've probably already covered 80 problems. Not really, but you know what I mean. It's just that it goes a lot faster when you kind of recognize what you're doing with it. Let's do another one. Let's try one with the other format. So I see one here that says 10n squared minus 59n minus 6. And in my head, I already got what it was because of the value and things like that. But now let's break this one apart. First of all, there's no greatest common factor. But this method is going to be the exact same. I know that my first term is going to have some form of n times n. The difference is this time 10 needs to be a combination of either 5n times 2n or 10n times 1n. Let me have those in certain colors. Or 10n times 1n. So here, 10 and 1. Now it's a little bit more difficult. I can't just guarantee a single lock-in of one number. And there are times where I can a little more so. I've talked about this concept of evens versus odds, but because 5 and 2 are an odd-even pair, because 10 and 1 are an even-odd pair, it doesn't work out that way, especially with 6 only having even-odd pairs. So that doesn't necessarily filter out which ones work. I know which one I'm going to try with more because of how large 59 is. I definitely want to try with 10s first. But let's say that I didn't and I worked with the 5s anyway. When it comes to just testing things out, there's still that whole negative product is maybe a plus here, maybe a minus there, maybe I switch them around. But when I do my FOIL thing, I know that if I combine a positive 59, I switch it back. All this conversation is just strategy on FOIL this until it works. And choose numbers of 6 until this thing works. Now, if I put 6 here and 1 here, 3 here and 2 here, those aren't the only tests to consider. You also have to consider 1 and 6 and 2 and 3. Because when you FOIL, 5 is going to multiply by this number, either 1, 6, 2, or 3. And 2 is going to multiply by this number, either 6, 1, 3, or 2. You know, if I do 5 times 1 and 2 times 6, versus 5 times 6 and 2 times 1 and add them together, or negative 6, whatever, I'm getting way different results. So now you have to swap them. That stuff doesn't have to happen with 1x and 1x. So again, I'm probably talking more of the factoring strategies involved in general. And you're asking, how do we know when to apply which method? I'm trying to tell you they're all the same method. The difference is, I know how to expedite this version of what you're looking at when it's just an x squared, when it's just an n squared, a 1x squared and a 1n squared and all that. Because, one more time, and then I'm just going to talk strategy the rest of the way. I'll do a couple problems and that'll be it. Because I know that x squared, listen, 1's not a prime number, but 1 only comes from 1 times 1. So there's only one factor combination. Because x squared only comes from x times x, then I know I've already locked that into place. Because I know that when I multiply 1x with another number, that number becomes my coefficient. That 1 is not going to change it. So my only focus when I get one of those, and I'll finish this problem later, but my focus when doing those problems like this one that you saw before was, I already know this is an x and x. Those are locked in, period. As long as it's factorable, those are going to be in the answer. There's no other choice. I'm really just looking at these two numbers, or I'm just imagining them. And how do I get these numbers? Same way as either method. Factors of this number. Factors of 6. 6 and 1 or 3 and 2. That's it. And switching them doesn't change my result here because x exists in both these. They're still multiplying by 1 no matter which way you switch them. 6 plus 1 didn't work. 3 plus 2 worked. Over here, so different. Not only is 10 a composite number of 5 and 2 or 10 and 1. Now we have to consider those things. But now, which number am I going to multiply 5 with or multiply 10 with versus 1 and versus 2 and all that kind of stuff is way different, first of all. Second of all, I forgot what my second of all. Oh, second of all, when I do my tests, I actually have to multiply that. I can't just do, what's 6 minus 1? Is that negative 59? No, what's 1 minus 6? Is that negative 59? No, 5 needs to multiply with one of the numbers first with my test. So there's a test involved. Now, I do a lot of that stuff mentally. You might have to use a calculator. You might have to write it all out. And for the sake of strategy here, or for the sake of process, I'm going to write these ones out. Then I'll talk about which ones I wouldn't have done. Then I'll maybe do one more example. So let's test these ones. 5 times negative 1 is negative 5. And keep in mind, it's negative 5n, but the point is they're going to combine to become the n's anyway, so I'm not looking at that. 2 times 6 is 12. Negative 5 plus 12 is not 59. Negative 59. It doesn't matter. Actually, honestly, I'm looking for positive or negative 59. It doesn't matter. 5 times negative 6. 2 times 1. That's negative 28. Little closer, but not quite there. But keep in mind, notice how switching the 6 and 1 drastically changed the result of what combined because of what it's multiplying by. 5 times negative 2, 2 times 3. 5 times negative 3, 2 times 2. Okay, none of those gave me negative 59. Or positive 59. Let's try with 10 and 1. Let's try 6 and 1, 1 and 6, 3 and 2, 2 and 3. I'm sorry, one of these needs to be a minus. All right, 10 times these values, 1 times these values. 10 times negative 1 plus 1 times 6. Remember, you got to keep them together. 10 times negative 6 plus 1 times 1. Okay, negative 60 plus 1 is negative 59. So the answer seems to be, actually the one that's most fitting in here right now. The answer seems to be that. That seems to be the factorization. 10n plus 1 times 1n minus 6. And that's the order too, the signs and everything. So that's the answer. We found it, right? So the test, remember, it's not negative 6 plus 1 which adds to this thing. It's that they have to multiply. But the strategy didn't change. Excuse me. The method didn't change. Just the way that I streamlined this method changed so much. Because these are just ones. And because I know that they're just ones. It's because I know they're just ones that I can put them there. Whereas opposed to right here, I don't know if it's 5 or 2. I don't know if it's 10 or 1. And it's because these are ones that it doesn't change these values when you multiply by these, so that when you add them together, it's just those numbers that you're looking at. As opposed to when you're looking at these ones, I didn't just do negative 6 plus 1. I did negative 60 plus 1. Why? Because one of them got multiplied by 10. You know, just like here, 5 times 1 versus 5 times 6. Whoa, way different values that come out as a result, you know? So it's just a thing to make sure you understand when it comes to method. I'm using this method for the other version, but it's more streamlined. You see, I can stretch out a power hour when you guys only ask 2 questions, but I hope it's making sense what I'm doing. Now, did I have to do all these tests? Absolutely not. First of all, like I said, as I was writing the problem, I said I already got the answer in my head. Reason being, negative 59 was so large, I knew that I wanted to multiply 10. I figured I wanted to try and multiply 10 by something to really grow it. In this case, multiplying 10 with 6 really grew it. You know, it got really close to negative 59. I got negative 60. So I got really close there. Multiplying 5 even by 6 didn't quite fit the bill when it came to size, or 10 by 3, you know, like that. However, strategy-wise, what other ones would have I considered even testing or not? Here's what I would have never tested. I never would have tested this pair, this pair, this pair, or this pair, on the basis that 2 and 6 would have had a GCF of 2, 2 and 2 would have had a GCF of 2, 10 and 6 would have had a GCF of 2, 10 and 2 would have had a GCF of 2. If your original problem does not have a greatest common factor, neither should your factorization. And if your factorization does, then that means it's not the right answer, or you didn't get your greatest common factor out yet, in which case you should have. So, whoops, let me still cross out those ones that I didn't want. So I'm going to eliminate those. Listen, honestly, anything else is fair game. But when it comes to my size comparison testing, I need to get negative 59. I know deep in my heart, in my head, whatever, that multiplying 5 with 1 and 2 with 6 ain't going to be enough to get me there. So I can test it. It's just not enough size. It's too small. Oftentimes we talk about something being too big for a test. This one's just too small. My first go-to is let's get big first. Let's try 10 times 6. If that doesn't work, I'll go 10 times 3, whatever, all that kind of stuff. So that's where I got to. And I did in my factoring factory video. I don't know how long I spent on it, and there's that. I didn't get to do any even odd stuff here. So let me find one more problem to do with you guys. Oh, and there's and then you might ask about the special case factoring also, and I'll get into that last. But as far as special case factoring, you can do it just like these. The difference is, just like the first question, do you know your perfect squares? So that you know that you can use that method of factoring just by knowing what perfect square trinomials and difference of two squares factor to by nature. Otherwise, you can go straight to your stuff. You can go straight to your stuffs before. So let me do one more of each type just for my factoring factory worksheet here. Let's see what there is. Okay, this one. N squared. Oh, that's a perfect square trinomial. We can still do it. It has an n. I'm going to write an x. X squared minus 12x plus 36. Once again, when I factor this one, I know that it's an x times x setup, and I know that my two numbers right here are also going to add to become that, just because it's a 1 and a 1. Positive product and negative sum also guarantees a minus and minus. This is all locked in. This is all locked in right here. I don't have to change these. If it's not factorable, I'll cross it out, but I don't have to erase anything. I know these are guarantees. And if this is like 18 and 2 or 2 and 8 or 2 and 18, whatever, switching, it's not going to change my answer. So 36 is so many factors. 36 and 1, 18 and 2, 12 and 3, 9 and 4, and 6 and 6. Well, 6 and 6 are the negative 6 and negative 6 are the ones that add to negative 12. All the other ones, if I tested them, negative 9 plus 4, negative 9 not minus 4 is negative 13, things like that. Very close, but not the answer. Negative 12 minus 3 is negative 15. This is the one that gets you there, so it is x minus 6 times x minus 6. Now, on a multiple choice test or something, if you saw this option, this would be the better answer and clearer answer, which brings me to my next point. This was a perfect square trinomial. This was 1x squared. This was 6 squared. And this was double 1x times 6, negative 12x. And so that factors into, again, x minus 6 quantity squared. So there's just that recognition of that. Now, which one's faster for you on this kind of problem? Maybe the first version that you saw. It depends on how big the numbers are. Let's get one more kind of problem, and then I'm just going to call it quits from here. Let me scroll down. Let me scroll down to a random page. Let's look at, perfect, this one. 7x, okay, they have a letter r. 7r squared plus 36r plus 32. Let's factor this guy. So this one I can lock some things into place kind of like the previous set, which is nice. So check this out. I know this will be 7r times 1r because 7's a prime number. Kind of like 1. 1's not a prime number, but 1's only factors are 1 times 1. 7's only factors are 7 times 1. So I know that part's locked in. That's pretty nice. That's good. So this is kind of like one of those questions like that. And a positive product, positive sum. I also know this will be a plus and plus. That's great. The difference is when I do factors of 32, and I'm going to write them out over here. So like 32 and 1, 16 and 2, 8 and 4, 5, 6, 7. I think that's it. Are there more? I think that's it. Okay. The difference is when I write these in, I'm not just adding these to get to 36, and none of them do add to get to 36, because one of them is going to be multiplied by 7, right? 7 times 1, things like that. Plus, and now this one has a 1 on it, which is nice. 1 times something is just itself. So what are my options? 32 and 1, 16 and 2, 8 and 4, and switching them. 1 and 32, 2 and 16, 4 and 8. Now let me show you what I'm going to eliminate without even considering its test. I am going to eliminate the 32s and 1s, not because of too big or too small, although 7 times 32 is too big. It's because that's an even odd factor pair, and I'm going to multiply something plus multiply something and add to become an even number. This is only going to be possible through an even plus an even set. That means only even factors of 32. This is another strategy conversation to be had. So anything here is fair game. I am going to eliminate 7 times 16 from my set and 7 times 8 from my set. So my only two valid tests I'm going to try are just these two. 7 times 8 is 56. 7 times 16 is double 112. So I'm only going to be trying these ones, really. So let's try 7 times 2, so that's 14, plus 1 times 16, which is 30. Not bad, but not correct. Now let's try 7 times 4, plus 1 times 8, which is 36. So it's not that one, but it's that one there. So it becomes 7r plus 8 times r plus 4. So the test about two numbers that add to become this and stuff are fine. It's just it's not only these two numbers. They get multiplied by that set. And that comes through. So all of these things, guys, they all have that method. They all have that method. The reason we brought up the diamond earlier was that was a visual aid to represent the specific question we were asking at the time, because those answers appear in that form. And I know I'm repeating myself. I understand it. I fully acknowledge that I am. But I want to hit it home with every new example that I get. And these ones aren't as simple as a diamond, because one of your numbers gets multiplied by 7 in this case. And you got to figure out how that works. And switching them around changes your result. The good news about 7 was 7 only comes from 7 times 1, which is nice. 32 had several different factors. I got to eliminate one of them. I got to eliminate some possibilities on the premise that it would just be too large to add to 36, which is nice. Only 2 tests at most, and it's good. Now, I know that wasn't really one of the questions with regard to factory strategies, but that's it. And guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching this power hour, or at least 36 minutes or something like that. And yeah, good luck with the things that you do. If you want to check out that factory video, it's just me going super fast through a bunch of different factoring and strategies, some of which you haven't really done before, but that is all fine and all good. One the same. All right, guys, thank you. Take care. I will see you in the next one.